We will look into sound intensity, okay, and then the problem solving involving with sound intensity. Okay, so for the first example, okay, we have a fundamental tone, okay, sound given has a frequency of 500 hertz over here, okay, so this is an important information, okay, and then they wanted to determine the frequency of the first harmonic, second harmonic, okay, the first overtone, and for the second overtone. Okay. First question for all harmonic that exist, and then B for odd harmonics only. Okay. Okay. So the fundamental frequency F naught given as 500. Okay. By applying the equation and F naught. Okay. So for all harmonic, that means you will have a order of n 1, 2, 3, and onward lah. Okay. So the first harmonic n will be equivalent to 1. Okay. So therefore the frequency will be equivalent to the fundamental frequency lah, okay, which will be 500 Hz. Okay, for second harmonic n will be equivalent to 2. Okay, so by replacing in the value 2 we get 1000 Hz. And then for first overtone, okay, so when we have first overtone n will be equivalent to 2. Okay, so we have fundamental frequency. After fundamental frequency we will have first overtone. So n will be equivalent to 2. We will end up with 1000. Okay, and then second overtone n will be equivalent to 3. Okay, which will end up with 1500. Okay, now for odd harmonic. Okay, so odd harmonic, that means the number of harmonics will be in arrangement of 1, 3, 5 and onward. Okay, so for the first harmonic n will be equivalent to 1, okay, which will end up with 500. Second harmonic n is equivalent to 2. So does this harmonic exist over here in odd harmonics? Okay, we don't have n equivalent to 2 over here, right? Because the value of n over here will be equivalent to 1, 3 and 5, this value only. Okay, we don't have 2 available. Okay, does not exist.
I didn't understand that.
Okay, so for first overtone n will be equivalent to 3. Okay, therefore we will end up with 1500, and second overtone n will be equivalent to 5. Okay, which will be equivalent to 2500. Okay, so for example 10.8, you have a loudspeaker radiates sound wave uniformly in all direction. Okay, at a distance of 3 meter, the intensity of the sound wave is given as 0.85 watt per meter square. They want you to calculate the power of the loudspeaker and then the sound intensity at a distance of 6 meter from the source. Okay, so for solution A, we apply the equation of intensity, which will be equivalent to power over area. Okay, so over here the power is already given, and the area of sphere. Okay, so area of sphere will be equivalent to 4 pi r square. Okay, so now we are referring to the first distance, which will be 3 meter. So we label as R1 lah, okay, which will be 3 meter. So replace in the value, okay, intensity given. So therefore we can determine the power, which will be equivalent to 96.1 watt. Okay, and then since the wave is originating from the same source, okay, so the power will remain constant. Okay, power will remain constant, and then it will affect the intensity as it moves away from the source. Okay, so that means now the new R will be equivalent to 6. Okay, apply the power which you have obtained in A, so replace in to determine the new intensity. Okay, so which will end up with 0.2, okay, watt per meter square. Okay, so for the next subtopic will be application of stationary wave. Okay. Okay, so for example 10.9, okay. So example 10.9, you have a stretch wire, length given 80 centimeter, mass given 15 gram, vibrates transversely. The wave travel along the wire at the speed of 220 meter per second. Two antinodes can be found in the stationary wave formed in between the two fixed end of the wire. Okay, so for the first thing what you should do is that sketch and label the waveform for the stationary wave. So based on that we can determine the wavelength of the progressive wave, okay, and then frequency and also the tension. Okay, now for the drawing. So these are the information given: velocity, length and the mass, okay, convert into SI unit. Okay, so for the drawing, so you have a stationary wire, so this will be one end, and then this part over here you will have another end, okay, and then you should have one, two antinode, okay. So over here they have stated that you must have two antinode, right, over here, okay, you must have two antinode, okay, can be found in between, and then the total length is at 0.8, okay. Okay, so basically if you observe this diagram, at 0.8 you have two antinodes. That means it will make one complete oscillation. So that means this length will be equivalent to lambda, right? Okay, so this one will be basically equivalent to lambda, your wavelength. Okay, so by referring at the figure, basically L will be equivalent to lambda. So therefore lambda will be equivalent to 0.8. Okay, so and then by applying the equation of wave speed, okay, v equal to lambda times f, okay, we can determine the frequency, so which will end up with 275 hertz, okay. And then mass per unit length we can calculate, okay, mass per unit length, so mass already given, length given, okay, so which will end up with 1.88 times 10 to the power of negative 2 kilogram per meter. So you can apply that in the equation velocity, tension per mass per unit length, okay, root value. So from here we can calculate the tension, okay, so which will end up with 910 Newton. Okay, so for example 10.10, okay, you have a tube 80 centimeter long, closed at one end, okay, and then you have a resonant, and the vibrating air column in the tube produce sound of a frequency 1134 hertz, okay, 1134. And then the fifth overtone mode is found in the air column. Okay, they wanted to ignore the air, end correction. They wanted to sketch and label the waveform of the air column, and then calculate the speed of the sound in air and then the fundamental frequency. Okay, now for sketching process. Okay. Okay, so basically what we have over here is that fifth overtone, right? Okay, so if you refer over here, we will have fifth overtone. Okay, so if you calculate the antinode, okay, so it will be n plus 1 lah. Okay, so that means which you should end up with 6. Okay, so if you calculate back over here, 1, okay, 2, 3, 4, 5 and 6. Okay, so fifth overtone, so that means you will end up with 6 antinode lah. Okay, so that means you should end up over here. Okay, and then over here the total length is 0.8. Okay, so in order to calculate the wavelength, okay, you should be able to calculate, you follow this one over here. Okay, so one complete oscillation, so you have one lambda over here. Okay, another second complete oscillation, 2 lambda, okay, 2.5, okay, and then another quarter. Okay, so that means you have one complete oscillation, 1 lambda, 2 lambda, over here half, and then add up with another quarter lah. Okay, so that means 2 plus with another 3/4. Okay, so which will be equivalent to lambda. Okay, now for the solution from the figure, okay, L will be equivalent to 11/4. Okay, so therefore lambda will be equivalent to 0.291. Okay, and then for speed, okay, V equivalent to F lambda. So frequency given, okay, we already determined the lambda. Okay, from there we can calculate the velocity, which will be 330 meter per second. Okay, and then for the fifth overtone of a closed pipe, okay, so this one you can refer back at the notes. Okay, so we will have a odd order, so that means it will start with N1, 3, 5 and onward. So that means we have fifth overtone. So fifth overtone you will end up with order 11 lah. Okay, N will be equivalent to 11. Okay, so therefore F times okay, fundamental frequency times width, okay, n. So n is 11 over here. So determine the fundamental frequency, which will end up with 103 Hertz. Okay, next let us look into example 10.11. You have a 3-meter long air column open at both ends. Okay, frequency of a certain harmonic is 500 Hertz, and the frequency of next higher harmonic is 557 Hertz. Okay, they wanted to determine the speed of the sound in the air column, and then the end correction can be neglected. Okay, so these are the information given. Okay, length given, so the frequency for the first and then the second order. Okay, applying the formula for open pipe. Okay, now let's say first order, we just put it as F1, and then let's say order N1 lah. Okay, times V over 2L. And then let's say for second order, F2, we put it as order 2 times V over 2L. Okay, where the second order will be the first order plus 1. Okay, because it is situated next to the first order, so that means you will end up with N plus 1, the second order. Okay. Okay, so expand in, okay, you will end up with equation 2. Okay, so this one, what you can do is rearrange, and then you can replace into solve to find V lah. Okay, once we have these two equation. So this one, the first equation, they rearrange, okay, into equation 3. So equation 3, substitute into 2, okay, and then solve it to obtain the value of V, okay, which will end up with 342 meter per second. Okay, so for the last example will be example 10.12. You have a uniform tube of length 60 cm stands vertically with its lower end dipping into water. Okay, and then when the length above the water is 14.8 cm and again it is 48 cm, the tube resounds, okay, to a vibrating tuning fork of frequency 512 Hz. Okay, from here they wanted to calculate the speed of the sound, the lowest frequency to which the tube will resound when it is open at both ends. Okay. Okay, alright. So first what we can do is that based on the explanation given, we can draw okay, how the situation looks like. Okay. So we have distance L1, okay, which will be the first distance of the air in the tube, resonate with the tuning fork, which will be a fundamental mode. Okay. And then the next distance, okay. So we have a next distance which you can refer to as overtone, okay, which will be the first overtone. Okay, so by applying the information, okay, so for the first resonance, okay, and then for the first overtone, okay, so what we can do is that by minus, okay, equation 2 with 1, okay, you can eliminate the value of C. So from there we can determine the value of lambda. Okay, so this one involves N correction. Okay, and then once we have the value of lambda, okay, we know the frequency given, we can determine the velocity of the sound wave. Okay, and then to determine the base frequency or fundamental frequency, okay, so first what we can do is that we can determine the N correction, okay, by applying back to the equation 1, okay, L, lambda, all we already determined, so determine the value of C. Okay, so once you have the value of C, okay, replace it into equation to determine the fundamental frequency. Okay, so which will end up with 267 Hertz. Okay, alright, so that's all for this subtopic. Have a nice day.